No, all right. Well, we don't have a lot of people, but it's time to start, so I guess we'll start. We are we're on week 5. I noticed that I got a little bit when I looked back and looked at the syllabus, I got a little bit off on the syllabus because I think it's because I had on the first week in the lecture, I was able to basically cover most of the material for the operations one back here. So we're basically a week ahead, which is fine. So right now, today we're going to do terrain and surface modeling, and we're going to discuss utilizing terrain derivatives in the lab. We're not going to do this modeling water part. We're going to do that when we do surface flow and GIS. So we're on this week lecture and lab, even though it's a week ahead, which is great because terrain and water flow should actually go pretty well together. So we'll have them before spring break this way. So this will be great. So we're right here. Remember that we don't have a lecture next week, and because we don't have a lecture next week, we also won't have a lab next week. No formal lab. I'll still be here during the lab time. If you want to show up, we'll still dial down to the coast, and I'll be able to answer questions that you may have working through the labs that you have up to that point. But we won't introduce any formal lab topic next week. All right. So if you go back to the course website here, you'll notice that there's the lecture. You can go ahead and download that. I already have it up, so I'll just use that version that I have up. There's some example data that I'm going to work through today. And then there's a reading here, and this reading, you should read through it before we'll discuss the concepts in the reading. I should have posted it up there, but the lab will have some of those concepts posted in it, included in it. And so you should read through that reading before the lab. Okay. So this is the lecture for the week. It's a lab I'm working on for the other course. So I'm going to go ahead and open up another version of ArcMap. So I'll have that ready. The example data I have for this week's lecture is really the same as for last week's lecture, except I messed up when I assigned it a projection. So it's the same exact data as last week, but now I assigned it the right projection. So my fault. It didn't really matter for the demonstration last week, but it's been changed. Okay, so today we're going to talk about terrain modeling. This is a slide actually, or a graphic from the book that we used for the first course. But just as a reminder, we talk about terrain modeling and all of the different derivatives that we can pull from terrain data. Today we're going to explore those a little further. We're going to talk about some of the pitfalls using terrain data. We've already kind of mentioned some of those. We talked about just a second, I forgot to a little bit better for the people on the coast. We talked about how you need to pay attention to your units when you start calculating things, particularly when you start dealing with the third dimension. You can make sure your XY units are the same as your Z units, things like that. Let's get back to some basics here. We have the primary terrain model, which is a raster. We're talking about rasters in this class. There are other terrain models. A raster grid, where every grid cell has a number that represents the height above some datum. That's the primary thing. And all these other things are basically derivatives of the height data. And so we have a slope. Slope is rise relative to the horizontal distance. Talk about that a little bit. Aspect is actually the direction of the steepest slope. And then those are going to be the primary ones we'll talk about today. We'll also talk about visibility a bit today, and we'll talk about hill shading. We're going to leave the bulk of these, upslope area, flow length, upslope length, in the middle there to talk about next week. Well, not next week, the next time we meet in 2 weeks after Mardi Gras. Okay. One of the reasons why we're going to spend a lecture talking about this is that these height models, sorry. Okay, let's turn down. My ringtone is a sheep. Sorry about that. One of the reasons that we spend so much time talking about this is because height is, which is sometimes called a digital elevation model, is a very important layer in most GIS databases. We have lots of different sources of digital elevation model data. The LiDAR data, the data that I already showed you last week during the lecture, is LiDAR data captured using basically a system that bathes the Earth in laser range-finding measurements. We get an XYZ location wherever it touches the ground surface. But prior to LiDAR becoming widely used, probably the most popular method was photogrammetry. Photogrammetry is a little bit more manual method that requires taking 2 images from 2 different perspectives of the same area. And you can actually derive a 3D scene from that sort of information. It's done less and less often, but the skilled photogrammetrists would find areas where the terrain change was important for characterizing the landscape. So you would find the area where a slope changed rapidly and figure out what the elevation was along those areas where the slope was changing rapidly, and not worry about the areas where the slope was more consistent. And so you wouldn't have nearly the coverage that you would with a LiDAR instrument. Okay, we could get less than 1 point in a square meter using LiDAR. A photogrammetrist would have to spend a whole lot of time getting that because he's doing each one manually. But a skilled photogrammetrist could find areas, the sides of buildings, a cliff, a bank, those areas where the landscape was changing quickly, and choose those areas and determine the elevation in those areas, and come up with a fairly good digital elevation model. There are other ways to create digital elevation models. Radar is one. Radar does have the weakness that it's not the best at penetrating vegetation. However, if you get a long enough wave radar instrument, it will penetrate vegetation. So particularly in tropical areas or very large global studies, for example, the United States put a radar instrument on the space shuttle and acquired 30-meter DEM data for the entire, well, not the entire Earth, everything except for the extreme polar regions. So Antarctica isn't included, either as anything above about the same latitude in the north. So you can download that global, they call it the SRTM, the shuttle radar topography mission data, and that's actually pretty much the standard for a global digital elevation model data set. So we have digital elevation models that are very precise, very high resolution data, and digital elevation models that are very, very coarse. It used to be that the United States government actually downsampled that data from 30 meters, which was the original, the way it was collected, to 90 meters. Okay, so they were afraid of, I don't know if afraid is the right word, but they didn't think that it was necessary for people to have that data. That could be useful maybe for bad purposes. But that data recently, within the last 2 years, has been released to the public at 30-meter scale. So it used to be you can only get the 30-meter data in the United States. Everywhere else, it was 90-meter, but now it's 30-meter worldwide. And then kind of on the opposite scale there, if we talk about survey data, it is possible to create a digital elevation model, I guess, using field methods, using survey data. And this is actually similar to what I did for my dissertation. I took survey data and compared it to a digital elevation model that was created using LiDAR data for a small area. And so you can obviously get a very accurate data set using real-time kinematic GPS. In a similar manner that you do with photogrammetry, you'd have to find the good areas to calculate, to create a digital elevation model. Okay. So each of these different sources actually produces different types of error. In photogrammetry and survey data set, it really depends on whether or not you captured the key portions of the environment in order to have a good digital elevation model. With a LiDAR data set, it really matters how well you've processed the LiDAR points and thrown out basically the points that aren't really on the ground. Maybe they're caught up in trees or buildings or whatnot. And with radar, probably the least accurate by default, but it becomes the most practical way to do things because it's probably the cheapest in terms of cost out of each of these. And so if you're doing a very large area, on the scale of a continent or even a country, that might be the best option. Okay, so as I said, height is perhaps the most utilized GIS layer. It's used for water modeling, which we'll spend a whole lecture on next time we meet. It's used in conservation. That's one of the areas of research that I do. It's used in site planning, obviously, infrastructure development. It's a very important GIS layer. And we're kind of going about this a little bit, I wouldn't say backwards, but eventually we're going to talk about how to take point data, which is what you get whether or not you did a survey or a LiDAR data set, and convert it into an elevation data set. But it's also actually more of an advanced topic. So once we have a height data set, what we're going to do with it isn't quite as advanced as creating the data set itself. Now, once we have a height data set, there are actually many different terrain derivatives. But the most important or the most widely used are slope and aspect. Okay. Here's a little slide on how we calculate slope in general. Okay. Slope is just defined as the change in elevation. It's a rise with a change in a horizontal position or a run. Okay. So rise over the run. If you want to get the percent slope, you could just multiply that by 100. A over B times 100. All right. Now, if you want to get slope in degrees, you could use trigonometry to take basically the arctangent of A over B, and that will give you this angle instead of giving you the ratio as a percent. So A over B is a percentage, and this is degrees. Okay. All right. Okay, so that's in general, right? So this is just how we calculate slope of two lines. Well, now we're talking about 3 dimensions. This is what we actually have in a GIS system. We actually have numbers that represent elevation. So what is the slope here at point 44? Right there. What's the slope? Well, we can see in general that the slope is going in this direction, and we could kind of define it maybe as, 52, 44, 42. So we could come up with an average change in this direction, or should we use this direction? Should we use this direction and then that direction and average the two? There's lots of different ways that we can conceptualize this. It's a question that scientists have struggled with, is how to calculate a single slope value for each cell based on these numbers. Okay? And basically, there's 2 widely adopted methods for calculating slope. So we're going to talk about how these methods are arrived at, and what the implications of using a method like these are. So the 2 basic methods are to use, for the slope of this center cell, to use the 4 nearest cells. That's Flemmer and Hoffer's method. The 4 nearest cells are this one, this one, this one, and this one. So those are the cells that we're going to use. And then the third order finite difference is actually going to use all of the surrounding cells to calculate slope. All right. Now, in order to show you how this is done, review, we talked about this first week, we're going to review kernels a little bit. Remember that a kernel is a multiplicative factor in each cell of a moving window. And so every cell in a moving window gets multiplied by the value in the kernel. We can make our own kernels, and we demonstrated that. We'll do that in a second here in the lecture. But here's an example of a kernel that's used to average all of the values within a moving window. So it's going to multiply everything by 1/9, which is basically arriving at the average for these 9 cells. Okay. All right. And here's a kernel for doing a high-pass filter. I'm not going to spend too much time on this, but this one basically accentuates the positives and negative, the high positive and high negative values. I don't know what happened there. It just exited. Now this is the one that's closest to a slope kernel. In fact, both of these kernels together, the horizontal difference and the vertical difference, both of those kernels together, if we use them in conjunction with each other, we're going to be able to start forming the foundation of how the slope is calculated for a particular cell. You can see that this filter calculates the horizontal difference. So everywhere it goes, it just takes the cell on the left, multiplies it by 1, and the cell on the right and multiplies it by -1, and then adds those numbers together, which has the same effect as subtracting the cell on the right from the cell on the left. Okay? So you can see in areas where there's a change, right here, there's a change, we get a value of 40, because that's the difference between 980 and 940. The difference is 40. Here, the difference between 980 and 900 is 80, and so we get values of 80. Okay? And in these areas, likewise, in this kernel, likewise, we get values that are north and south instead of east and west, but it's the same. It's the same value. It's the same difference, meaning that it's the difference between the top and the bottom instead of the left and the right. But otherwise, it's exactly the same. So, how do we use this to calculate slope? Well, you can start to see that this value becomes the change in the rise. So 40 is the change in rise as you travel across these cells. the change in the rise. The change in the rise here is 40. Going north and south, the change in the rise here is 40 going east and west. Okay, and so what we're doing is for every grid cell, we're finding the change in the rise and storing it in one grid, and the change in the rise going a different direction in another. The north-south rise change here, the north-south rise change, and the north and the east-west rise change. Okay, so that's what this formula is basically doing. It's saying, okay, the change from here to here is 9. So 49 minus 40, that's what this kernel does. And it assigns a value 9 there. The change in the north-south rise is 48 minus 45, which is 3. So we get 3 divided by 20. And you'll notice that I didn't worry about the sign, okay, which direction it was. And that's because these numbers are going to get squared. Okay? It's part of the formula to square those numbers because we're finding a distance basically. Okay, so look at the divide by. We're dividing here by 20. Dividing these by 20. Remember what the equation is. It's the rise divided by the run. So how would we arrive at a value of 20 in this particular case? So we've got this, the difference between this cell and this cell is actually, we're looking at the third dimension, the change in height. This is the change in height. How would we get the change in run, or the change in the x measurement, or the change in the spatial position? How could we get that number? Let's think about a raster. A raster, all these cells are the same size, right? Okay. So what is the distance from the center of this cell to the center of this cell? Somebody said 20? Yep, that's correct. The center of this cell to the center of this cell is 20. The distance from the center of this cell to the center of this cell is 20. So that's where this other number comes in. So basically, all we've done is calculated the rise over the run here, the rise over the run here. That's what these numbers are saying. Rise divided by the run, which is 20. And we get a number, okay, that represents the slope in percent. Okay, this number right here. So 45 negative 1.5 is the slope in that direction. Now the next thing that is commonly done is to come up with the average slope somehow. Okay, and there's actually a few different ways that different algorithms do this. One method is to take the absolute values, add them together, and divide by 2. Okay, that would be averaging the slope this direction and the slope this direction. All right. Other algorithms, and more commonly this is done, take each one and square them, add them together, and take the square root. Okay, which has the effect of accentuating larger slope changes. All right, so and then finally, to get the slope as a degrees instead of as a percent, you would take the tangent, the arctangent of that number. Okay, so you can see that this process is actually pretty straightforward and could be done inside of ArcGIS, probably in just running 2 tools, because this could be a map algebra expression, and it's easy to create a kernel like this. So we'll demonstrate that really quick and prove that the numbers are very similar. Okay. and I'm not going to round out to the exact same numbers. Okay, now this is the one that's actually implemented in ArcGIS, this method of finding slope. So if you ask ArcGIS to find slope, it's a little bit more complex. I shouldn't say more complex. It just, the kernel is a little, it's really the exact same math, but the kernel is a little different. So instead of using a simple kernel where we're subtracting 1 on either side, okay, 1, and adding 1 on the other side, we're putting this third order finite difference function in, which is just a fancy way to say that we're using a kernel that takes the average of both sides but weights the center pixel more than the others. So I'm weighting this pixel more than I'm weighting this pixel, but I'm still saying, okay, in general, what's the slope going in this direction? And what's the slope going in this direction? I'm just weighting the center pixel more than the other two, but I'm still finding a slope. And I'm going to get a different answer. I mean, if you used a different function, you're going to get a different answer. Okay? So there's all sorts of different papers, okay, older papers. These are established methods now that look into calculating slope in different manners. Which one is better? Well, this is the one ArcGIS chose to implement when you calculate slope. So it's looking at all three of these numbers, but it's weighting this one twice as much as it's weighting the other two. Other than that, the formula is the same. So I'm just weighting this change twice, and then I'm dividing it by 80. Why would I divide it by 80 now instead of by 20? Because we're still only talking about 20 being the distance here. Well, the reason why I divided it by 80 is because now I'm talking about 1, 2, 3, 4 measurements. And so I have to multiply 20, which is the rise, by 4 measurements because I'm averaging it over 4 measurements. So this number 80 is really 2 times the cell size times the number of measurements. So again, I'm taking 1, 2, 3, 4 measurements across. Okay, it's the sum of the weights basically. See these weights? 1, 2, 3, 4. Sum of those times 2 times the cell size. Okay, so that's how I calculate the slope. All right, demonstration time here. So if I download the data for the lab, I put that in. I put that right here. Okay. Remember, this is the same data as last week, but now I actually stored it in the proper projection. I was wrong last week that it was in. I said last week it was in UTM zone something, but it's actually in Mississippi State Plain. Okay. The thing is that the place that I got the data actually documented it incorrectly in the metadata file, but they actually told you on the web page that they had done so. So I guess there's a good reason. So it's really in Mississippi State Plain East feet, and the way I can tell that it's in the right projection is ArcGIS actually allows you to add in base maps from other data sources from the internet, and they've created a number of base maps. So I'm going to add this topographic data in, and we'll be able to see that this data overlaps Hattiesburg, which is where I just actually took this from a Mississippi website. As soon as this draws, you'll see that it does that. All right. So this, see this, I mean, I guess you just have to take my word for it a little bit, but look at this creek, Boggy Branch Creek. That creek is in fact going up the center of this area. See that this creek, you can tell it gets lower right there, and so that makes sense. It makes sense that that would be a lower area where a creek has created a depression there. Okay, and you can actually see this railroad right here. You can see the railroad. Let's choose a different color ramp. Oh, too bright. Something like that. Maybe something like that. Oh, it's still going to be too bright at the top. Okay, I'm going to spend too much time on this. There's a good one. Try that one. Okay, that looks a little bit better. You can see that the berm that the rail line has created right there. So this is a rail line on the map from ESRI, and this is the berm. Okay, so it does match up. Not that you probably didn't believe me, but just showing you there. Okay, so we're going to calculate slope. The typical way, and we've done this before, is to go in here under Spatial Analyst and calculate under Surface. We're going to calculate slope. I'm going to calculate slope in degrees so that we can make the equivalent data set and show that it works. So I'm going to save this in the same location. Let's say week. Well, I didn't say where I calculated. I'm going to store it in here. This is last week's one. So we're going to call this DEM slope. I already have that. I'll call it DEM slope degrees. Save that and run it. The XY dimensions are actually feet. The Z dimensions are feet, so this will work great. So I calculate this and I get slope. Okay, it looks kind of weird. The areas where the slope is rapidly changing, like right here, are where we get higher values. So how would we, if we didn't have that function, or we wanted to learn, which is what we're doing here, we wanted to learn how that's calculated, we could look at just a plain old neighborhood function. And neighborhood functions are actually implemented in all sorts of software. In fact, they're implemented in some image processing packages. So you could build a slope function right from those neighborhood functions if you had that. So under focal statistics, if you input your DEM, you can save this as, I'm going to call this DEM NS change or rise. So the north-south rise. Okay. And then we need to select the weight, and we need to make a kernel file. Okay, remember, we're talking about kernel files. We're going to make a 3x3 kernel, and the north-south kernel is going to look like, let's make it like these. So the north-south kernel is going to look like this. It's going to look like 1, 2, 1, 0, 0, 0, -1, -2, -1. So what we've done here is created a kernel that's going to calculate this number for us. So I'm going to say File, Save. I'm going to save this as, I'll just save it right here in my, you can save it wherever you want, but you have to keep track of where it is because you're going to need that path if you're following along. You don't have to follow along if you want to pay more attention. Either way, it's fine with me. In the lab, I would always suggest following along. But I am recording this, and so it will be there. I'm going to call this north-south change and save it. Okay, so if I go back to ArcGIS now, and I choose my kernel file, I don't know why it doesn't let me actually choose it. I think that's a bug or a lame feature. Okay, I can say where I want the kernel file is. And then one other thing, when I demonstrated this before, I forgot to tell you, you could change the statistic type. So at the end, you could choose whether or not to have it add up all the numbers, which is sum, which I think should be the default, or whether you wanted to take the average value or even the standard deviation. I think sum should be the default. So what it's going to do is it's going to create the numerator here. It's going to multiply all of these values by their kernels and add them up. So it's going to do that. See how we're adding? It's going to add them up just like here. So it's going to create the numerator, and we're going to have to create the denominator portion because we don't want to divide it by 80. I mean, we don't want to use mean because the mean would not divide it by 80. It would divide it by 9. Okay, so we do the sum. Let's see, what's it saving this as? Yeah, saving as north-south rise. So I'm going to run it, and I'm going to get an interesting data set that looks like this. Okay. All right, and remember that it's looking for changes that are running north-south and accentuating those changes. So you can see in these areas, it's bright as it's facing north. Okay, so I'm going to do this again, run focal statistics. I'm going to input the same digital elevation model, and I'm going to save this now as east-west rise, or EW rise is what I'll call it. Okay. Choose weight, and make sure this says sum, because I may actually forget if I don't do it now. And then I'll go back to my kernel and just adjust it so that it looks like this kernel here. Negatives on this side, positives on this side. So I'm going to do something like this. 2, 0, 0, 0, negative 1, 2. Oh, this should be negative. Now this kernel looks like this kernel, and I'm going to file save as EW change. Now, these file names don't really matter. They're just helping me remember, because I do have to put that back into ArcGIS. So now I say C:/temp /EW change.txt. If your kernel file isn't formatted right, ArcGIS will tell you about it. It'll say, that's not a properly formatted file. But if you just put the wrong numbers in, it's not gonna tell you that. Okay, so now this one looks more like the sun is shining in this direction because we're looking at changes in the east-west direction. Okay, so you can see the edges of the railroad tracks and so on. So we've got these two data sets, right? And what we need to do is to use map algebra to create that big old equation, and we'll be all set. So if we look at this equation here, this is not quite done. We still need to get the distance. When we need to square them, add them together, take the square root, and find the arctangent. So that's a lot of numbers, but we can do that by first, let's take each one of these. We're going to add them. We're going to end up adding them together. But before we add them together, we have to do what first? We have to divide them by basically 2 times the cell size times 4. The cell size in this case, anybody know how I look that up? I just go like this, properties, and I can look under, I can look under source. The cell size is right there. It's 5 by 5, 5 feet by 5 feet. So I say, what's 5 times 4 times 2? Oh wait, it's 2 times the cell size. What's 2 times the cell size? 10 times 4. 40. Yep, 40. Divide each of these by 40. Then I have to square them. So the function's called square. See right there? It's called square. So I can type in square, and I got to put it inside the parentheses. So I'm going to square this one and square this one. I'm squaring them, and then I'm going to take the square root. That's the next thing. Sometimes that's tricky, but taking an exponent to 0.5 is the same thing as taking the square root. Okay. All right. So right now I'm up to this point. I've taken the square root of this number, and then the last thing I need to do is do the a tan of that whole thing. And I believe that's also, yeah, that's also going to be in there. See, using this one right here. Okay. The arctangent. Okay, so we'll save this as slope degrees 2. Let's say save. And there's going to be a few differences, particularly on the outside edge with the way it's calculated. But this is going to run through, and the numbers will be very, very similar. There'll be some rounding number changes. Oh, I forgot to do one thing. Let's just run it again. You could always go under geoprocessing, results. And you'll notice that the numbers that it produced are all really small. That's because I forgot the final step. To get real degrees, I have to multiply this by 100. That's part of the, because this is actually going to give it to me although that's not in this function. It's to get the real number, you multiply it by 100 because this is a percent rise. And to transfer between percent and degrees, multiply it by 100. Okay. So now these values should be very, very similar. If I type identify and I say visible layers here, and I turn everything off except for the slope layers, and I click it, I get a value of values that are similar. What did I? Maybe I was wrong about the. Just a second. Multiplying it by 100. The numbers were pretty similar, but they weren't exactly the same when I did the slope times 100. Okay. Make sure I got all my parentheses right. Well, they're not exactly the same, but when I do this, when I do it like this, we do get pretty similar numbers. Yep. All right. I might have messed up somewhere. Let's look at my kernels. Those look good. Oops. Yeah, that looked good. Okay, well, I do have to figure out exactly how I messed up, but you could see that it produced. It's messed up in a linear fashion. Everywhere where this shows a high value, it really is a high value. It's just not producing slope in degrees. But it is producing slope. See how these in fact, if I symbolize them using the same symbology, we would have very, very similar values. Probably this one. Okay, so this DEM compared to this DEM, let's just flip it. Invert. Okay, so this one compared to this one, they look almost exactly the same. You know, the colors aren't exactly the right colors, but we're getting very similar. The slope's high everywhere where the slope's high. So that's how ArcGIS calculates slope. And obviously, I've just entered a number in wrong. I did it before class, and I did it right, but whatever. Maybe I used the wrong division sign, or squared. I squared them. Yeah. So if I was, I'm going to take time in class right now, but if I was going to figure out what I did wrong, I'd try each of these steps individually and check out what I did wrong. But anyway, we could arrive at slope for those data sets. Okay. All right. So that's slope, and one of the issues with calculating slope in this manner is that first of all, as I've already pointed out, the formula that you use to calculate slope will produce a different result. But one thing that's actually even more troubling is that the value for a slope for a particular area will actually change depending on the DEM you give it. And that'll be the last thing I'll demonstrate here really quick. So if I have this original DEM right here, let me turn off this layer and this layer. If I have this DEM, and I take this DEM, and let's say I had the DEM from the shuttle radar topography mission, from the SRTM data. So I had the same DEM, multiply it by 1, but environments, what I'm going to do, about how many feet are there in 30 meters? About 100? So I'm going to put 100 here. Change the cell size from 5 to 100. And I'm going to say OK here. I'll just call this DEM 100. Save it and run it. So now I have the same digital elevation model. Okay. This is actually the exact same one. I just resampled it, and you can see now. You can see the cells up there, right? See the cells? Now, if I calculate slope from this data set, calculate slope, and I won't go through my method. I'll just compare it to, whoops. So I'm going to use this DEM 100, and I'm going to call this slope degrees 100, calculate slope, run it. Looks good. Now, everywhere I click, if I click, right here, and I look at I want to turn on just the 2 slope maps, click right here. The slope degrees 100 is 6, and the slope degrees is 4. I go over here, I get some similar values. Oh, look how off that one is. It was one that was off by 3 or 4. In fact, I could basically subtract the 2 DEMs and figure out how far off I was. And what's really interesting, overall, look at the change in slope. In the original slope, it went from 0 all the way to 65. The highest slope was 65 point something degrees. In this data set, the highest slope became 12.9. Okay, why did that happen? Why did the highest slope go all the way from 65 at the high, all the way down to 12, or basically 13? Think about why might that happen just because I used larger cells?
The runs.
Yeah, the run is very, very large. Okay, and so although the math makes sense that slope should be calculated as rise over run, if we use a method like this, we're really changing the maximum possible slope a lot by changing the size of the grid cells encompassed. And so when you're tackling a particular problem, you need to think about that. And so like if you're trying to say, okay, well, the reason that I'm using slope is to find out how quickly water would travel between or through these cells. And in that case, you might say, well, I'm justified in using this number because this is kind of like the average number. So it might be that, you know, in this area, there's a really fast slope and it travels quickly, but then it kind of tinkers out. But it might not work because you might really be concerned with not necessarily the average, but the maximum speed that water would travel in those areas. And this wouldn't produce that result really well because you're getting an average value. You're not learning anything about the slopes in between those 2 points. You just know the average slope in between the center of every cell. That's a pitfall of using slope data because it's a derivative of the elevation data. It's really influenced by the elevation data that you utilize to create that. All right, aspect. Aspect is the orientation of the slope. And we won't go through calculating this in ArcGIS, but it's calculated similarly. It's basically the next derivative. So we're looking at, this is the change in Z divided by the change in Y. And then this is the change in Z divided by the change in X, and you just you just divide one by the other, take the arctangent, because now we're looking at the direction, the compass heading direction of that slope. Okay, so instead of looking at the slope, we're calculating the aspect. And what it produces is a number between 0 and 360. So it's still in degrees, but it's telling you which direction it is. If the slope actually is purely flat, ArcGIS will give it a negative 1, sorry. So in other words, if all 1, 2, 3, 4, 5, if all of the surrounding cells, all 8 surrounding cells have the same value, the aspect will be -1. Okay. If any of them have a slightly different value, it won't be -1. Okay, viewshed. A viewshed is a method that calculates the area that's visible from an observer. And this is a bit of a complex algorithm, but I can explain it pretty easily, I think. So what has to happen, the first thing that happens is that from the viewpoint, whatever the viewpoint is, okay, we calculate the triangle from the height of every cell back to that triangle. So we calculate the angle. So each cell is assigned an angle back to the elevation of the original point. So based on the distance, which we could use find distance for, and the angle, then we could calculate if any of the intermediate points were interrupted by by another cell in the data set. So basically it traces that ray back along. So for every cell, it traces the ray back, and if it hits a cell before it gets back to the viewpoint, you can't see it from that location. Okay, so that's how the algorithm works inside of ArcGIS. So basically, you get a grid where every single value is a 1 or a 0, meaning that it's visible or not visible from the given viewpoint. Because it relies on, not because it relies on find distance, but find distance is one of the inputs, and you can see why you have to input a viewpoint for this to work. So the viewpoint is kind of like the source in find distance. Okay. So you get an output like this, where all the visible areas are coded in 1, everything else is coded either in no data or 0. And we'll practice this in the lab. All sorts of applications for viewsheds, planning the location of something that needs a view. Also, there's lots of military applications for viewsheds. Either looking at vulnerability or looking for a place for an ambush. So basically the people shooting or the people getting shot at would both need to know what the viewpoints are or what can be seen from a particular location. So that's the application of viewshed. Okay. Shaded relief works by simulating surface illumination given a compass area and a horizon, a compass direction and a horizon. So where is the sun coming from? And there's two different types of hillshades that are often created. The first is what we call a cartographic hillshade. And a cartographic hillshade doesn't worry about the true position of the sun. We're more concerned with making a hillshade that looks good. In fact, if I go back to ArcGIS here with my original digital elevation data, here's my original DEM. If I create a hillshade here of this data set, the defaults here are 315 and 45. That's a cartographic position for the sun for most of where we would deal with. Okay, so if you think about on the horizon, 0 being north, 315 is looking back up into the northwestish area. Okay, the 360 would be back to north. So 315 and then 45, the sun would never be up there. The sun would never be over there. Okay, but if I hit OK, what this does is creates a hillshade that looks very, very good to our eyes. That we understand. We understand. We read right to left. Maybe it has to do with that. For whatever reason, this makes a hillshade that's easy to recognize. Whereas if we changed the value for the digital elevation model and change this to something that where the sun might actually be, maybe 1 or maybe just not 90. That'd be so 270, 230 might be a more reasonable value. The sun would be over there like the setting sun. If we did that, we get a hillshade that looks that can play tricks on our eyes. Okay, so here we've got a data set, and it's harder to tell which way is up. Okay, these are two different visualizations of the same data. Okay. And if the sun was ever like in the southern sky, we would get 180. I'm gonna change the Z factor a bit so that the shadows will be the shadows will be stronger. Okay. Again, this would be a cartographic hillshade just by definition if I change the Z factor, but you can see here, coming from the south, our eyes start to play even more tricks on us as to what's positive and what's sticking out of the landscape and what's going into the landscape. Okay, so that's a cartographic hillshade. A cartographic hillshade is just a pretty picture to make it look like there's that you're looking at one of those hard copy maps that's bumpy. An analytic hillshade is something that you would use to maybe model where the sun was hitting the earth more often. So you might be modeling a certain plant species. Where would it live? Well, it might be one of those plant species that actually needs a certain amount of sunlight every day. And so if you set up ArcGIS to run a hillshading technique for as the sun moved across the sky and then added up all of those values, you could see which areas got enough sunlight during the day to sustain that plant. So that'd be an analytic or analytical hillshades, depending on who you talk to. One's more preferred in the United States. So here's a shaded relief model. An example, this is a cartographic relief model because it's headed from this direction. All right, second here. Okay, so that's slope and aspect and a few of the other models. And now we're going to discuss another method for calculating information about an elevation data set. And that is referred to as calculating the surface normal vectors for a digital elevation model. And these were first proposed back in 1999. And what's unique about this method is that we store the slope and aspect data together. Okay? And it's derived from linear algebra and cartographic modeling. So this can be implemented in cartographic modeling. And basically, the reason that we would do this is that storing, first of all, there's a few reasons. One is that in areas where we have flat slopes, we get undefined values for slope and actually for aspect. Okay, there's no slope in those areas because we divide by no, we don't divide by 0, but we have 0 over the run. So we get 0 values for slope and undefined values for aspect. And this method allows for comparisons to be made directly on overall angular differences rather than individual values. What does that mean? Well, here's a crude diagram that I made. But basically, if let's say that these two these two lines represented the connection point between 3 cells. There was a cell here, there's a cell here, and a cell here. There's a cell, and there's an elevation value. We could say that the elevation here is 1, the elevation value here is 2, and the elevation value here is 1. Okay. If we were to calculate the average slope across this area using the traditional method, we would get the average slope value would be 0. Okay? I mean, sorry, would be the average. Yeah. Well, let me back up there. Okay, these aren't actually the center of each cells. This is just a digital elevation model that goes up and then it goes down. Okay, goes up and then it goes down. So the average across this entire area would be 50. So because the cells on this side would be all 50, and the cells on this side would be all 50. And so we would get an average slope of 50 degrees. Okay. If we use the surface normal vector, the average of cells pointing in this direction and the cells pointing in this direction is going to be 0, because in this direction is exactly opposite of this direction. And so we could say that the average slope is in fact 0. Which one's correct? Well, neither one of them is correct. They just might help us answer different types of questions. Okay? If we're really concerned about a particular set of questions, like, you know, which direction is the slope facing on average, the second one is going to be better. It's facing almost north on average. Whereas the first one would be better in a situation like, let's say that we're concerned about how fast water is flowing over these areas on average. Okay, how much erosion potential there is. Then the first one would be more beneficial. Okay. All right. Here's a few other. I guess these aren't really reasons, but these are how it gets done and how easy it is to implement. Basically, the way that this is done, it's based on linear algebra. We'll walk through the technique, but it's pretty straightforward implementation based on mathematical formula, and we can see that here. Okay. So the way that we get our surface normals, and I should explain what they are. I haven't. I should have put a better slide in. The surface normals are if I have a surface, if I made a surface that looks like this, I'll just draw it right here. If I had a surface that looks like this, now let's say these are cells. This is the center of each cell. Okay. So the surface normal is going to be if I had a little thing, a little stick sticking out of the center of the cell, okay, and it was exactly 1 unit long. So I've got a stick sticking out of the center. That's what we're going to call the surface normal vector, and it's normalized because it's 1 unit. So it's 1 unit long. I have an x, y, z position here, right? I have an x and a y, and the z is elevation. This value right here also has an x and a y and a z. If this is sticking out always perpendicular to the cell, okay, always perpendicular, I've got an x and a y and a z value. And as this angle changes, the x and the y and z value change. If it's straight up, in other words, if it's a totally flat surface, the x and the y and the z value are what? Well, the x and the y are the same as this x and y, if it's straight up, right? So this x and y right here is the same as this x and y. And the z value here is 1. Z equals 1 because it's 1 unit above this unit. Okay. Now in this case, z is less than 1 because it's really, we can figure out the math here. We won't do it, but we'll show you what it is. Okay. If this is 1 right here, this distance right here is 1. Okay. Then we know. And this angle is 90, we know what these distances are. We know what this distance is, and we know what this distance is. And this distance actually becomes the z value here. Okay? So as the slope gets higher and higher, z gets lower and lower. Okay? As the slope gets more and more, z gets that difference between this z and this z. It's normal because this is 0, 0, 0. Okay? So that value gets lower and lower and lower. And x and y get higher and higher and higher as you move out, as you increase the slope. And then as you change in this direction here, like on this side, x and y would be large positive numbers. X and y would be large positive numbers. This direction, x and y would be large negative numbers. Okay. So how do we actually make those numbers work? Well, it's actually pretty easy. Okay. We'll practice this a bit in the lab, but what we do is, first off, we take slope and aspect the traditional way. We calculate slope and aspect the traditional way in ArcGIS, and then modify those slope and aspect values and just use trigonometry to figure out the x, the y, and the z values. So the sine of the aspect times the sine of the slope gives us where the x would be. The cosine of the aspect times the sine of the slope gives us where the y would be. And the reason that these work it just goes back to trigonometry. You may or may not have taken a trigonometry class. Even the ones in high school, though, you probably learned with right angles that you can figure out the distances of the other legs of the triangle using trigonometry. Okay, and then finally, the cosine of the slope gives you the z. Because remember, we said that the z value would be directly related to the slope. So as the slope increases, the z value gets closer and closer to 0 as the slope increases. Because a perfectly straight up and down line will produce a value that is close to 0. In fact, we could prove that real quick. Let's say, okay. I don't know what I have open in Excel. Okay, so if I have a value of 45 for a slope, and I say equals cosine of 45, I get 5.2. Now, if I have a value of 0, cosine is going to give me 1. Okay. So you can see that if I go back to here, remember in this diagram, which I got rid of the annotation, but if it was totally flat, z would be 1. It'd be 1 because it would be 1 unit off of the ground. Now, if I have a value of 1, the cosine is going to be 0.54. So that's 1 degree, sorry. If I have a value of 90, then the cosine is going to be negative 0.487. So the z is going to be a little bit negative. All right. And it's going to move through being 1 all the way down to that area. All right. Let's go back to here. So this is the actual cut and paste from the reading from the article that talked about surface normal vectors. Okay. And then this is that implemented in Model Builder. Okay. So I implemented it in Model Builder. I actually built this model. We'll use this model in the lab. So we'll run the model in the lab and create our X, Y, and Z grids. Okay. So you could see all that I had to do was take the input raster. You can change the cell size optionally. That's something that I added as a parameter. But really, all you need is the input raster. It calculates slope. It calculates aspect, and then by default, it calculates those values in degrees. So I converted them to radians. You could actually change that. You could actually change that method so that it just calculated in radians to begin. Oh no, it only calculates in percent. So you can't. So we had to do this degrees to radians conversion because this expects those numbers to be in radians. Actually, that's probably why my numbers weren't working really well in Excel. You probably noticed that a little bit. But so you convert it to radians, and you get cosine, the sine. The cosine of the slope turns into your z grid. The sine of the slope is one of the things that I need to get my y grid. The other thing that I need is the cosine. Okay, the aspect cosine. And then this little hammer is really a map algebra function that takes the sine and the aspect and adds them together, multiplies them together right here. Okay, and then I calculate the y grid and I get an output. So I have one input and 3 outputs, X, Y, and Z. And on Thursday we'll practice using this data set. Maybe modifying. Actually, we will modify this model that I built together to do this. Okay, so we're basically going to figure out how to calculate the average slopes and see how they're different than calculating the average slopes using the traditional method. Okay, and then look at where we would apply those in different areas, because you can basically get a different answer. Are you calculating the average slope for a region, or are you calculating what the average individual slope values are? Okay. Those are the 2 types of questions that you're answering. So the way that you do a zonal operation is that you would have to calculate the sum of each of these. So we'll implement this. Calculate the sum of each of these in Model Builder, the zonal sum, and then figure out what the mean slope and the mean aspect were for those entire areas. You'll get a different answer than taking the zonal sum of the slope originally. So that's how that's implemented. All right, and again, we'll practice that more in the lab. I won't demonstrate that right now because I will do that in the lab. All right, did you have a question? All right. Anybody else have a question about what we covered? We're in about 10 minutes early, I guess. So, but I did record it this week. So if anybody, we did have a lot of people filter in here. Looks like we got 2 people down on the coast. I'll go ahead and stop the recording there. And